In this video, we're going to prove a fact about the image of connected sets under continuous functions. So the theorem says, let E and E prime be metric spaces, and let little f from E to E prime be continuous, then if E is connected, so is the image f of E. So this is saying that the image of a connected set under a continuous mapping is connected. So let's prove it. Well, connected means that you cannot write the set as the union of two disjoint non-empty open subsets. So when you have something like that, it's often better to work with the condition of being not connected. Because if you're not connected, then there are two disjoint non-empty open subsets whose union is the set. So when you have something like that, then you can actually work with those open subsets. So because of that, it actually would be easier to prove the contrapositive statement. So we will prove the contrapositive. And what is the contrapositive of this statement? It's that if f of E is not connected, so suppose that f of E is not connected, will show that E is not connected. So since f of E is not connected, we can write f of E as the union of two disjoint non-empty open subsets. So we can write it as A union B, where A and B are disjoint non-empty open subsets. Open subsets of f of E, right? So these are open in f of E, in the metric space f of E. Okay. Well, now what can we do? We can take the inverse image, right? We want to write E as a disjoint union of non-empty open subsets. So therefore, E is the inverse image of A union the inverse image of B. So now we've written E as the union of two subsets. Well, first of all, are these disjoint? Can you have something in F inverse of A and F inverse of B? Well, no, because if you didn't, suppose that you had X in both of them, then f of x would both be in A and B, right? So these are disjoint. So maybe I can write that down. If it's not obvious, it might be a good idea to write it down. So these sets are disjoint. Okay, because if not, let x be in the intersection, then f of x is in A and B, contradicting the fact that A and B are disjoint. So these are disjoint. Now, how do we know that they are non-empty? Well, A and B are both non-empty by hypothesis. So if A is non-empty, okay, so we know that A is non-empty. So let's say Y be in A. Well, A is a subset of f of E, so there exists X in E such that f of X equals Y. Well, then X would be an element of F inverse of A. So F inverse of A is non-empty. Similarly, okay, you just do the same thing for B. So F inverse of B is also non-empty. All right, why are these? So we have disjoint non-empty subsets. Now, how come these are open? Well, these are open because F is continuous, right? And so the reason is because F is continuous and A and B are open. So since A and B are open and F is continuous, and we have this fact that the inverse image of an open set under a continuous map is open, the inverse image of A and the inverse image of B are open. Okay, so maybe we should write down that fact. So since A and B are open and F is continuous, okay, and the inverse image of an open set under a continuous map is open, F inverse of A and F inverse of B are open. So therefore, we've written E as the disjoint union of two non-empty open subsets. Therefore, E is not connected. And that proves the theorem, because we proved the contrapositive. So now we know that if you have a connected set and you look at the image under a continuous map, the image is also connected.